which means I can write this as MA equals minus A partial F over partial X dx. Okay, now watch carefully. What is my A? A is partial squared eta over partial t squared. It's the acceleration of that little segment moving back and forth, which is equal to minus A partial F over partial X dx. What did I call M here? Can I plug that back in there for M? Yeah? Rho A dx partial squared epsilon over partial t squared equals minus A partial F over partial X dx. Will this go away and that go away? What am I left with? Rho partial over partial t squared equals minus partial F over partial X. Now I'm going to go back to my definition of Young's modulus. Young's modulus was defined as what? Can somebody tell me? May I write this as, for this case, y equals F, because we defined F as force per unit area, over, what was the original? This was the change divided by delta x, not this delta, dx. Is that true? So may I replace this in here? What will I get? Rho partial epsilon over delta t squared equals minus partial over partial x of partial epsilon over partial x, y comes out. I can do that if I just write this as y partial epsilon over partial x. Can I do that? And what will this become? Rho partial epsilon over partial t squared plus y partial epsilon over partial x squared equals 0. May I also, you should do this in another step. May I also write this as over rho? Any objections? Now this is a second order partial differential equation. Yes? Yeah? What's the solution? What does this represent? Does it not represent that? It's speed. People have taken differential equations, right? Oh my God. Of course, I shouldn't expect people to remember it.
I'm just currently in.
Okay, so do you not do that when you have problems like this? Have you not done that for a spring? Where was omega equals square root k over m? Do you not remember doing that? For a spring?
That looks like
two people, yeah.
With frequency.
Yeah, well, it's the same. It's the angular frequency. It's the same thing, the same logic. That is just how we solve partial differential equations, second order partial differential. So speed of a longitudinal wave is given as, you will see this a bunch of times. Woohoo! And we usually put a subscript L to represent it. You could also do the same thing for transverse wave, exactly the same logic, but for a transverse wave, instead of a y, you usually get eta. So I'm not going to make you do the whole thing. Just remember, at this step, instead of a y, you will get an eta. And the definition of it, I'm just going to give you the definition. You should probably write this down somewhere. It's going to be eta over rho, square root. You see the similarities? One just has a y and one just has an eta. Also, thing to remember, VL is usually greater than transverse velocity. Also, you could do the same derivation for longitudinal waves if you use the bulk modulus. I am not going to make you do it, but you should know this answer. Write this down somewhere. You see the similarities developing? One was y, one was eta, but now that you have the bulk modulus, it'll also have the eta with it. Oh, also, if you have liquids, so I know this is not part of this chapter, but if you have liquids, liquids are always in 3D. So which one of the modules should you think you should be using?
Oh.
There we go. This was, oh, by the way. Okay?